This is part 4 of section 6.4. And what we're going to do now is we're going to start doing some operations on position vectors. So if we're given that vector v is -1, 2, and vector w is 3, -2, we want to calculate these things. Okay, the first thing we're asked for is to find the magnitude of w. Well, we talked about earlier back on page 5 of these notes that vector v, the magnitude of that, was equal to the square root of its components squared. So if we're asked to find the magnitude of w, this will be equal to the square root of the two components squared and then added together. So 3 squared plus -2 squared. So this is equal to the square root of 9 plus 4. So this is the square root of 13. Okay. Now, if we want to add v plus w, well, our property up here says that if you're adding two vectors, you add their component parts. So the vector v plus w will equal -1 plus 3. And then 2 plus -2. So this is the position vector 2, 0. Again, make sure that you are not using parentheses here, because if you use parentheses, then you're talking about a point, not a vector. Okay, now 2w minus 3v. What I'm going to do is I'm going to calculate 2w first, and then 3v, and then I'm going to subtract them. 2w, this is scalar multiplication. And we know that scalar multiplication, you multiply each component. So 2w would equal 2 times 3, which is 6, and 2 times -2, which is -4. 3v will be 3 times each component of v. So this will be 3 times -1 is -3. And 2 times 3 would be 6. Now, 2w minus 3v will equal, subtract 6 minus a -3, so 6 plus 3, and then -4 minus 6. So that answer will be the vector 9, -10. Now our next problem asks us to find the magnitude of 2w minus 3v, which is exactly what we calculated here. And if I hadn't already done it, I would need to get this answer. But you'll find that a lot of problems do this, where they'll have you figure part of it and then ask you to find the magnitude of that answer next. So here, if I want the magnitude, all I have to do is to take the square root of the sum of these two things squared. So 9 squared plus -10 squared, which ends up being the square root of 181. And I'd simplify that if I needed to, or if I'm asked to round it, but this square root doesn't simplify, and if they're looking for the exact answer, that's it. Okay, so now let's talk about unit vectors, which are also very useful topics. A vector of length 1 is called a unit vector. So just so long as it has a magnitude of 1, we're good. It doesn't matter what direction it's pointing in. If it has a length of 1, it's a unit vector. Okay? Now, sometimes it's going to be useful to find a unit vector that is in the same direction as another vector. Okay? So how do we do that? If v is a non-zero vector, okay, so we want it to have some sort of length, we can't do anything with a zero vector. You can't turn a zero vector into a unit vector. But then the unit vector, u, is equivalent to 1 over the magnitude of v. And remember that this part, the magnitude of v, is a scalar. Okay, because magnitude gives you a whole number, or not a whole number, a real number. So this will be a scalar value times a vector. And what it's going to do is it's going to change it to something that has a unit, it's going to point in the same direction, but its length is going to be 1. Okay, so let's work a problem with that. We want to find a unit vector that u in the same direction of this vector v, which is 5, -12. So to find the vector u, the unit vector, we have to know the magnitude of v. So the magnitude of v will equal the square root of 5 squared plus -12 squared. And that ends up being the square root of 169, which is 13. Okay, so the unit vector is equivalent to 1 over 13 times vector v. So what this means, this is scalar multiplication now. In scalar multiplication, you multiply each of these by this value. Our unit vector is equal to 5 over 13, -12 over 13. It will point in exactly the same direction, and if you were to find the magnitude of this, you should get 1. Okay, so now we have some special names for unit vectors. Okay, the unit vector, some particular unit vectors, I should say. The unit vectors that lie along the positive axes on the coordinate system are defined as followed. The vector I is 1, 0. I is along the x-axis, and it is 1 unit long. It starts at 0, 1 unit long. J is along the y-axis, and it points directly up, and it's 0, 1. Now, remember, X and Y go in alphabetical order, I and J go in alphabetical order, so that can help you remember which one goes with which. In Calculus 3, you will start talking about 3-dimensional coordinate systems, and you will have another unit vector that would be equivalent to coming up off of the page. That's just looking forward a little bit, okay? We call the unit vectors I and J standard unit vectors, and they're on this graph, okay? Now, one of the good things about this is that we can represent any vector in terms of I and J. So just look at this, okay? So if I have a vector v that is v1, v2, and we know vector addition, we just add the two components. So I could do v1, 0 plus 0, v2. So v1 plus 0 is v1, 0 plus v2 is v2. So this is the same, okay? So this is true by vector addition. And then we can take these values out because the scalar multiplication says you multiply each piece by this. v1 times 1 is v1. v1 times 0 is 0. So these, and the same thing happens here. 1, 0 is the vector I. 0, 1 is the vector j. So basically what this says, if any vector you have here, you take the first component with an I and add to that the second component. That's not a vector with j, and j is a vector. Very easy to do, okay? So the scalars v1 and v2 are called the horizontal and vertical components. v1 goes with I, and I goes on the x-axis, and that is the horizontal. v2 goes with j, which is the y-axis, which is the vertical component. Okay? So if we can do it like this, we rewrite it everything like this, then the magnitude, since these values are the same as these values, it's all the same. So if you're asked to find the magnitude of a vector written in ij form, you just take the coefficients, square them, and add them together, then take the square root. Okay, so an example problem. I want to find a unit vector, u, in the same direction as v, the vector v, equal to negative 12i minus 5j. This is the position vector, negative 12, negative 5. To find the unit vector, I need to find the magnitude of v. And the magnitude of v will be the square root of negative 12 squared plus negative 5 squared. And just as above, this ends up being 13. On a previous problem, we had different signs, but once you square them, it doesn't matter, and you end up with the same value. Okay, so now we're going to multiply this scalar times this. So our v value, just like we would multiply everything by 1 over 13 here, we're going to do the same thing here. So this is negative 12 over 13i minus 5 over 13j.